Okay, so last time we talked about a couple of things that were weird, right? This time we're going to talk about escape velocity and orbits, okay? Last time we just talked about what force of gravity generally looked like. And remember what I told you back then? I told you that for um, potential energy, where do we want to set that equal to zero? It all of a sudden starts making sense to set that equal to zero where there's basically no force of gravity acting on you anymore. You're such a distance r away. Your r is so large that there's no more force of gravity from the Earth working on you anymore. Okay? If you set that, that's where your potential energy is equal to zero. Way far out there at some point where you no longer feel the pull of Earth. Now that point doesn't actually ever exist. You can never actually get to that point. You can be on the far side of the universe and you'll still feel the pull of gravity from the Earth. However, we're going to assume that it gets so close that as your distance, remember, potential energy on a graph this way, your r on a graph this way. As you get so close to infinity, your potential energy falls off and it almost, but doesn't ever quite touch zero, right? So we're going to assume that it's close enough to be zero at infinity, okay? So that's where we set potential energy equal to zero is at infinity, okay? Well, here's where things get interesting. If you're hanging out there, deep, deep, deep in space, you're never going to get pulled towards Earth. You're never going to fall towards Earth. So guess what? You've hit escape velocity. When you are that distance away, you will take, if you are hanging out here, right, you'll never get pulled towards Earth. So what does your velocity need to be at that distant point to get away from Earth? Your velocity velocity escape, has to be 0 meters per second. You don't have to do anything. You're already outside of the pull of Earth. You're done, right? So what does that mean? If we were talking about it in terms of kinetic energy, what would the kinetic energy of you be at that point? Your kinetic energy at that point would be also 0 joules. So if you're already at that point, your total energy, remember this, total energy, we had work in there too, but really what we talked about, and rotational, but again, we're going to forget about that because we're talking about a straight line distance away from something now, okay? So don't worry about rotational energy, don't worry about work. The two things that really always kept coming up were kinetic and potential energy, right? Well, if you're already at infinity, total energy is 0 to keep you out there. You've already won the game, right? So you don't have anything to worry about. On the other hand, what happens if you're on the surface of the Earth? Okay, what if you're actually here, though? Instead, you very much feel that apparently your arm is growing out of your leg, which is awkward. Okay, there we go. That's slightly better. Okay, so if you're on Earth, you actually have to give a lot of energy to get the heck away, right? You got to get out. You want to get beyond the pull of Earth's gravity. So how in the heck do you do it? Well, you're going to have a high velocity to get there. But where are you ultimately trying to reach? You're trying to reach the point where force of gravity is 0, okay? So you want your total energy to still be 0. So the minimum point you can possibly get to, right? If you give too much energy, you're going to go flying off at some velocity, right? Beyond that. So you're still going to have kinetic energy if you get a little too much velocity, right? If you don't have enough velocity, your potential energy won't be enough to get to 0. So you're still going to fall back towards the Earth, okay? So what is the minimum velocity where I will just escape Earth and stop, right? It will come to a stop rather than continuing to go on with some velocity. So for that, here's what we need to know. Our total energy, okay, has to be equal to 0. And total energy has to be our kinetic plus our potential, okay? So that means 1/2 your mass times your velocity, your escape velocity squared, has to be, plus your potential energy, which again here is m, and now this is weird, right? Because this, if you remember the last time around, what we had was force of gravity, right? Which was mmg over r, that distance away from the Earth, right, is your potential energy now squared, times that distance away from Earth, right? So you ended up canceling out one of those r's, okay? So you end up with that. So that's your potential energy formula now. But also remember this. We're setting potential energy to be 0 when you reach that far distant point. So every other potential energy you have up until that point is actually below 0, right? Here's 0 right here. So you're actually negative, okay? So we don't have a plus there. We have a minus because that minus that is going to be equal to 0 when we get to that far distant point and just come to a stop. So really what you can see we need to do now is we need to set these things equal to each other if we want to find the escape velocity. Okay? So, if we want to find that escape velocity, the velocity you need to have to get beyond the pole of Earth, we have to do this. You get 1/2, or bring this to the other side, so we'll bring this one over to the other side, okay? So, mv squared escape, okay, is equal now to little m, mass of u, right? Mass of the Earth, gravitational constant, which never changes, over that distance to get basically to that point where you'll never come back, okay? So if you want to find your escape velocity, well, first off, your mass is on both sides here, so it cancels out. That goes away, easy enough. We got to get that 1/2, we got to deal with it, so bring it to the other side. We get rid of it here by multiplying by 2, so we got to multiply that side by 2. So we get 2 mg over r, and that goes away. We want to find escape velocity, not escape velocity squared. So what we do is we take the square root of both sides, and voila. Anytime you want to find escape velocity from any planet or the moon or anything else, this is it. Mass of the large object, gravitational constant, which never changes. Remember, g was 6.67 times 10 to the negative 11th, very small value. And then the radial distance away, the distance you actually have to get to escape velocity, okay? So that right there is actually not the radius of the planet, but actually the distance to get from their center of the planet to wherever it is that you will no longer feel the pull of gravity, okay? That's your escape velocity. It takes a lot of energy to get there, okay? A lot of energy. We've only actually, as a species, done it a couple of times, and that was basically to get to the moon. Every other time when we've gone into orbit, guess what? That object is not actually at escape velocity. It's still, if we let it go, it's going to go around in an orbit around the planet. So it's actually still bound to Earth, right? I take that back. As a species, I guess sending people, we've only ever sent people to the Earth, to the moon, right? And that's when people have gotten beyond that. We've sent probes all over the solar system, so they've gotten to escape velocity. That's where we're sending people. Very, 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 very few times have we ever actually gotten somebody to escape velocity. Okay. Everybody else falls into this category where they go up to the space station, or maybe they go out a little farther, wherever, right? Wherever they've gone to, they've still been bound to the Earth. They haven't actually hit escape velocity. So you don't have to get that fast to get to space. You have to get that fast to get away from Earth. Okay? So how do you find out what the velocity, if you want to reach, the space station out here, right? How in the heck do we figure out what velocity you need to hit to get to that distance? Well, this velocity here, okay, we'll call it v, that's our tangential velocity. Okay, so the speed doesn't change, right? We're going to have the same speed, but the direction will change, the velocity will change, right? So when we get out there, think about what's going to happen. When you get out to that point, you're going to get, well, I should have left that up. Rewrite that. Okay, we are actually going with that one. R infinity 0. Okay, so get rid of this for a second. Get rid of this for a second. But when we get you out to that space station, okay, how in the heck do we figure out how fast we've got to send you to get you up to that distance, okay? Well, that distance now, to get to there, we're going to call, that's our big R now, okay? To get you from Earth up to the space station, we've got to go some R distance away from the center of the Earth, okay? It's not the radius of the Earth. This is a very different thing. This is the height of the satellite above the center of the Earth, okay? To get you there, we've got to take, you've got to have a force of gravity still, right? If you're out there, you're still bound to Earth, so you still have a force of gravity. So if we do force of gravity, we're going to do Newton's version of it, right? The expanded version. Mass of u, mass of the Earth, gravitational constant over the distance to get you out there squared, okay? Now you're still bound to the Earth, okay? You still have a negative potential energy, okay? You're still stuck here, but you're stuck out there instead of here, okay? So how in the heck do we get you there? Well, we have to have another force to balance you out if you're not going to get sucked back towards Earth, don't we? So what's the other force that's working? Well, you are going to be going around and around and around while you're out there. So your velocity out here, right, is going to give you a centripetal acceleration. So, to keep you out there, this right here, force of gravity, has to be equal to force of centripetal, okay? And how do we find that? Well, if you remember, centripetal force is a mass times an acceleration, and our centripetal acceleration was v squared over r when we were talking about a linear tangential velocity, right? Omega was slightly different. Okay, so v squared over r, because we don't know our linear velocity. All right, so let me plug all this back in, put it back together. So for centripetal, I'm going to plug in v squared over r for AC here, v squared over r, and this is, again, the distance from the center of the Earth, right, over to that satellite. So that's what the centripetal force looks like. And now I'm going to plug these two things in together. So I'm going to go ahead and erase this so don't forget to get that down. Okay, review the video if you need to. Okay, let me get rid of this. Okay, so let me plug that in place of centripetal force here. mv squared over r, okay. Force of gravity, I'm going to plug this right here, this in place of Fg, so I get mass of U, mass of the Earth, gravitational constant, over distance to the satellite squared. Now, if we want to find the velocity it takes to reach that, well, how do we find that? We have to solve for v, right? So let's go ahead and do that. Multiply my mass over. Well, sorry, it is multiplied here, right? It's multiplied there. So I got to divide my mass out on both sides. Divide both sides by mass. Mass goes away there, divided by mass here, mass goes on the bottom, that goes away. So we get rid of that little m, okay? It goes away from both sides. There it is, okay. So we're getting closer to finding v now. So how do we now find it? Now we got to multiply both sides by that r value, right? Okay, r goes away here now. And one of those r's goes away down there. So there we go. Well, now we wanted to find v. Okay, we wanted to find v, not v squared. Okay, so v, to get to the orbit, to get to the orbital velocity, we got to take the square root of this, and we got to take the square root of this. So it turns out to find the orbital velocity, you need square root of the mass of the Earth, okay, times the gravitational constant, divided by the r, the radial distance from the center of the Earth over to the satellite. That's your r value. Okay, so that's how you find the velocity to get to a certain orbit. And by the way, when you're still orbiting the Earth, this is called a very important term here. It's a special kind of orbit. It is a bound orbit. Okay, a bound orbit as opposed to an unbound orbit. An unbound orbit is where you will eventually just keep on going rather than coming back. Right? Bound orbit does this. Unbound orbit does this. Right? And then eventually keeps on going. So if you had, in that other case, a velocity that was actually higher than your escape velocity, you would have an unbound orbit. You would keep on going. You'd keep on going farther and farther out. And if I draw you a picture of what that looks like, we've actually just, in the last year and a half, 2 years, kind of cool, we found a couple things that have unbound orbits. And what those things were was essentially asteroids and comets from other planetary systems. So if this was their planetary system to begin with, they might have had this really wide orbit. They might have gotten kind of picked off by something way out here. So instead of returning on that trip, they actually got kicked out here and kind of went flying, right? And so now that, now that encounters our sun over here and gets kind of sucked towards it. But again, it's going too fast, so it actually never hits. It may change direction, but then it keeps on going, right? So that would be an unbound orbit, something that's actually never coming back to its original position. It never actually stays in orbit, okay? That would be an unbound orbit, okay? Bound orbit is what you guys think of when you think of a satellite, though. Something going around and around and around the Earth. And that's it for this video. Escape velocity, bound orbits, and that's it. Voila. That's all for gravity.